Hello everybody, welcome to Unit 5 in the course on Embedded Systems Programming. In this set of lectures, we are going to look a little deeper into concepts in communications in embedded systems. So, we are going to start by reviewing what is the importance of communication protocols in the first place in the context of embedded systems. So, what are the kinds of embedded systems that we can think about? Let's look at a few examples over here. One of the areas where we might want to design an embedded system or an embedded set of devices rather than just one particular system is going to be, let's say, for home automation, and typical applications in the area of home automation would look something like this. When you have overall the structure of a house, you may want to sort of control lights and fans or air conditioning, in general heating, cooling sort of appliances. And at the same time, you also want to monitor the temperature in the house so that it does not go out of control. Now, normally the way that's done is, if you have an air conditioner, you set a temperature setting on it, and that's about the level of control that you get. But modern home automation systems can go one step further. They can actually even detect the presence of a person in the room and adjust the temperatures accordingly. They can change the temperature depending on the time of day. If necessary, they can anticipate when the person is coming home, or they can get a message saying that the person is on their way, and make the cooling or heating systems kick in appropriately so that it is ready just in time for the person and saves energy overall. Apart from that, you also have security applications where, for example, there are connected doorbells where even if the person is not at home, they can get a remote image of who is there and possibly even unlock the door if necessary. Now, when you have such an application, you have many different sensors, which could include motion sensors, temperature sensors, and so on, which need to be sent to a central control system. And you have the actuators. By actuators, in general, I mean something which causes either movement or at least a change in state. So, for example, when I turn on a light bulb, there is technically no movement, but there is a change in state from dark to bright. So, all of these commands would be received from a centralized control system. And one of the goals that we might have over here could probably be, we don't want to sort of run new wires for each and every one of these things that we want. Now, you could possibly make use of the fact that bulbs, fans, air conditioners, everything already has a source of current, because after all it needs electricity to work in the first place. Is there a way we can use that in order to communicate? And in fact, that is one of the things that is one of the communication protocols that does exist, although we will not be looking into that in detail. One other property that you might notice over here is that the data rates are typically low. You are just giving sort of a on or off condition and maybe a temperature sensor once a minute or something like that. It's not a huge amount of data. So, this sort of is an ideal scenario for, let's say, a wireless communication protocol, where I could have a centralized control sitting in one place. I don't want to pull a whole lot of new wires all over the house, but at the same time I need to be able to communicate back and forth. There are protocols such as Zigbee, and for that matter even just Wi-Fi or Bluetooth may also solve the problem for you. These are names that I am just sort of dropping at this point under the assumption that you have most likely heard of some or all of them, right? But the exact details don't matter. The point is, it is a wireless protocol, which we will be talking about a little bit later. Another kind of scenario would be industrial automation. A lot of factories follow a model whereby they have some kind of a conveyor belt along which some objects to be assembled are moving, and there are robots at various points in that factory floor whose job is to modify the object under construction in some way, right? Now, these robots first of all need to be precisely timed. The conveyor belt needs to be running at a certain rate, and I want to make sure that the robot is exactly able to sense when the object is present in front of it, respond and finish its task before the object has moved past where it was supposed to work. So, this requires a fairly fine-grained level of control. In particular, if there is a problem anywhere on the belt, I immediately need to instruct this to maybe skip that particular piece of the object under construction, and I also need to be able to shut everything down very rapidly if it looks like there is a problem somewhere. In other words, precise timing and synchronization between the different devices under control is necessary here. The other thing that you can imagine is that a factory floor is a noisy environment. Now, this is not really noisy from the point of view of the audio noise that humans might find noisy. As far as the electronics is concerned, we are talking about something called EMI, electromagnetic interference, right? And EMI basically says that if you have electronic systems and you have like large sources of current being switched in some parts of the factory, those large current switches cause radiation of electromagnetic energy, which in turn can get picked up by minute electronics and can cause them even to flip their state from 0 to 1 or vice versa, and in general to go wrong, right. So, the noise that we are talking about over here, in other words, is electromagnetic noise, and factory floors, because they are dealing with large motors which are switching large currents, very often do tend to have a large amount of electronic noise. Protocols such as CAN, the controller area network, are designed to be robust against such kind of interference, and at the same time they can generate high speed communication in a deterministic fashion. So, that is another example of the kind of communication that we might want in an embedded system. Yet another thing might be an application such as smart agriculture, where perhaps you have 2 or more fields that are at distant locations, and you want to be able to control you want to be able to sense certain things such as maybe the moisture, the temperature, carbon dioxide levels, the acidity in the soil, and so on. And you want to be able to take decisions on maybe when to turn on a sprinkler, when to do certain kinds of pest control, or maybe changing the acidity of the water that's being used over there. All of these are being done over fairly large ranges, assuming that your farm is fairly big, which means that you are dealing with a long range communication in an outdoor environment. And in such a scenario, there are many different kinds of protocols, primarily wireless, because you don't really want to be running long wires across farms just for the communication aspects. And at the same time, there are some that are better suited for outdoor communications than others. So, the key idea that you can notice through all of these examples is that we are talking about a scenario where there are multiple different devices that need to communicate with each other. In many of the cases, there might be one single centralized control system whose job is to basically accept data from each of these devices and to then send out control commands to each of the devices as well, right. But if you are just talking about a single embedded system like a calculator, then it probably doesn't need any kind of communication, but that's not the typical scenario over here. In fact, the term IoT, Internet of Things, essentially recognizes this fact that the maximum utility from embedded systems comes from the fact that there are many of them that are communicating with each other, and therefore they are able to work together and come up with better responses to the kinds of scenarios that you have to deal with. So, in this context, what is the role of a communication protocol? Right? We are going to start with sort of looking at what we mean by communication protocols, and then sort of see how to sort of go forward from there, right? So, there are a few things that a protocol sort of establishes. One of them is just functionality. How do I transfer information? So, it sort of makes the ability to exchange information feasible. Now, a protocol by itself is useless if I am the only person sort of designing and claiming that I want to use this protocol. I need to make sure that others are willing to interoperate with me, right? So, if I design a protocol and nobody else is willing to sort of standardize on that protocol, maybe the voltage levels they want to use are different, or the data rates are different, or the way by which a particular pattern of transmission starts is different, that's enough to break the protocol, and nobody else will. It loses its utility. So, we don't want to keep reinventing the wheel. So, therefore, we would prefer to standardize on a few protocols. Why a few protocols? Why not just one? Well, that's because there are different usage scenarios. It turns out that the kind of optimizations that you would use in order to have timely and fast delivery of data in a closed indoor environment with short range data and minimal electromagnetic interference is very different from the kind of protocol you would need when you want to communicate over long distances outdoors without the ability to draw wires across the system. So, there is a need for multiple standards, multiple protocols, Having said that, it is not entirely clear which one, there is no such thing as the perfect protocol either, right? So these are things which continuously do get updated and improved as people identify shortcomings of existing protocols, which is why you will see that there are ways by which there are multiple sort of versions of the standards that keep coming out. There are a couple of other important properties of communication protocols. One of them is related to scalability. How well does the protocol scale? Can I use this protocol in order to communicate with a large number of devices, or is it restricted to maybe 5 or 10? If it does a great job with 5 or 10 devices but completely falls apart when I go, let's say, to 40 or 50 devices, then it has its use case, right? It's not that it's immediately to be thrown away, because there might be scenarios where I actually only want to communicate with 5 or 10 devices. On the other hand, there may be protocols whose main purpose is to connect millions or billions of devices together and at least enable communication between them. Obviously, they cannot have the same kind of properties. Another very important aspect that comes about, especially in the context of embedded systems, even more than in general communications, is real-time operation. Now, as I have mentioned before, real-time does not necessarily mean very fast, right? All that it means is there is a time constraint which could be on the order of milliseconds or tens of milliseconds, which, if you think about it, is not very fast because computers operate on nanosecond timescales, right? So fast for a computer would probably mean something on the same time scale that it operates at, which means nanoseconds or at worst maybe microseconds. Whereas real time could very well mean milliseconds, because even if I'm trying to do something like avoid a car crash, I usually have somewhere in the order of milliseconds to respond, because of the physical nature of the devices with which I'm interacting. So real-time operation is something which keeps coming up in the context of embedded systems and is something that needs to be carefully planned if your application requires it. So there are a few different types of protocols, and what we will be doing in the rest of these videos is to sort of break them up and look at some of them in a little bit more detail. Now, even though I have put down a lot of names over here, the first thing I want to emphasize is this is by no means exhaustive, meaning that I have not covered all possible protocols. I may not even have covered all the most popular protocols. There may be something that you actively use which is not even covered in this. The point I am trying to make over here is just to sort of have enough of a high level overview of the different kinds of protocols so that you are then able, when faced with a new protocol, to be able to understand its properties and hopefully gauge where it can be used and how to use it. So what we will be looking at would be serial communications, parallel communications, wireless communications, networked communications, and one particular thing which is entirely restricted to the area of embedded systems, which is the field bus. We'll look at each of these as we go forward.